Alright, today we're going to be deriving the three kinematic equations for constant acceleration in one dimension. If I can get my marker to work. There we go. Let me write them out for you guys really quick. First off is final velocity is equal to initial velocity plus acceleration times time. Number two is displacement. That's equal to initial velocity times time plus 1/2 the acceleration times time squared. And number three is time independent. We have final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. So for number one, all we have to remember is that velocity is the first order derivative of position versus time. So that's change in position over time, and acceleration is the second order derivative, so change in velocity over time. Multiply both sides by t, we get at equals delta v. Delta v is just change in velocity, so that's final minus initial velocity. Let me rewrite that really quick. At equals final minus initial velocity. I'm going to add initial velocity to both sides, and we'll get v equals v naught plus at, and that's the first equation done. Sorry if I'm writing kind of small, but I don't have that much area to work with, and I'd like to try to do this in one take, so we'll see how that goes. I think I should have plenty of space, but anyway, to get to number two, all we have to do is integrate this equation with respect to time. So let's go ahead and do that really quick. We have the integral of v. Actually, before I do that, just so you guys know why we're integrating that equation with respect to time, if you don't know, because it doesn't take much time to explain, and just give a little bit of understanding as to why we do that. So let me plot velocity versus time and say that's our graph. If we take the integral of this, think about what you're doing when you take the integral of a graph. You're basically summing the area of all these rectangles, and that gives you a near perfect approximation of the area under the curve. So let me pull one of these out to work with. I choose this one. The width of that rectangle, assuming they're equally spaced, is dt. And the height of that rectangle, we'll say, is f of t. So f of t correlates to some velocity output right here on the vertical axis. So it has units of velocity, and the horizontal axis has units of time. So the area of this rectangle, we could say, is f of t dt, but the units of this rectangle would be velocity times time. And if you remember what I said right here, that velocity is a change in position over time. If we multiply both sides by t, we get velocity times time equals displacement. And that's why when you integrate this first expression with respect to time, you should get displacement on the left-hand side, and the right-hand side should be equal to that. And vice versa, if you take the derivative of that right-hand side, you should get equation number one back. So we'll go ahead and do that right now. We'll take the integral from t equals 0 to t equals t of final velocity, and that equals the integral from t equals 0 to t equals t of initial velocity plus the integral from t equals 0 to t equals t of acceleration times time. It looks a little complicated, but this is the easiest integral in the world. Final velocity is a constant, initial velocity is a constant, and acceleration, the one condition for these three equations is that acceleration must be constant. So that means there can't be a third order derivative of position versus time. The jerk must be 0. So you can pull all the constants out of the integral, and it becomes very simple from there. So v times the integral from t equals 0 to t equals t of just dt equals initial velocity times the integral from t equals 0 to t equals t of just dt plus acceleration times the integral from t equals 0 to t equals t of t dt. This is just equal to vt on the left-hand side. On the right-hand side, we have v naught t plus at squared over 2. if we rewrite Vt on the left-hand side as change in position over time times time, we should get delta x over t times t, and the right-hand side is exactly the same, plus 1/2 at squared. I just pulled the 1/2 in front to make it look a little bit more like equation 2, but yeah, we cancel this t with this t, and equation number 2 pops right out. We have displacement equals initial velocity times time plus 1/2 acceleration times time squared, and you're done with that one. And then for equation number 3, it's just algebra from here. If you'll notice, equation number 3 does not have a time variable, so we just have to solve for t in equation number 1, plug that into equation number 2, eliminating time, and equation number 3 should pop right out. So let's do that. If equation number 1 is v equals v naught plus at, subtract initial velocity from both sides, then divide by acceleration. We have v minus v naught over a is equal to t. So we'll plug that into equation number 2 now. Displacement equals v naught. Looks like my marker's dying on me now. Let's see if I can just get it to work for the next 3 minutes. V minus v naught over a plus 1/2 a v minus v naught over a squared. A little bit of algebraic simplification here. So we have delta x equals v naught v minus v naught squared over a plus 1/2 a times v squared minus 2v naught v plus v naught squared, if you FOIL out that numerator, all over a squared. Multiply by 2 to clear that fraction, as well as this a cancels that second power in the denominator, so we get 2 times the displacement equals 2v naught v minus 2v naught squared plus v squared minus 2v naught v plus v naught squared, just enough space there, all over the first power of acceleration. Multiply both sides by a, so we get 2 times acceleration times displacement equals 2v naught v minus 2v naught squared plus v squared minus 2v naught v plus v naught squared. And then we have positive 2v naught v, negative 2v naught v. We have a minus 2v naught squared and a positive 1 v naught squared, so that's going to cancel with that, and we get 2 times acceleration times displacement equals minus v naught squared plus final velocity squared. Add initial velocity to both sides, and final velocity squared equals initial velocity squared plus 2 times the acceleration times the displacement. Alright, so there's those 3 equations derived. Not every physics professor requires that you know how to derive these, but you should always know where your equations come from, because if you don't, you might miss out on some potential physics. So leave any questions you have in the comments, and thanks for watching.